Yes, sir.
Electric potential. Electric potential is the work done in bringing the charge from infinity to that point. Okay, the work done in bringing the test charge from infinity to that point is called as electric
Potential.
potential. Okay, the SI unit is now this is joule and this is coulomb, joule per coulomb or
Inverse.
volt.
Cool. Yes,
Okay,
sir.
or volt. Okay, now here electric potential, positive potential, you have negative potential. The positive charge gives positive potential, negative charge will give negative
Yes,
potential. So for a point charge, electric potential due to point charge. So if I consider a point charge, okay, so I'll consider a point charge. Okay, now this has got a charge Q. So at a distance r, at a distance r, distance is r.
yes, sir.
At a distance r,
Yes,
the potential due to this point charge is kq by r.
yes, sir.
Okay, if it is having negative charge, you will have negative potential minus kq by r. If it is having positive charge, then plus kq by r.
R. Yes, sir.
Okay, then potential potential of potential due to system of charges,
Yes,
due
sir.
to system of charges. Now if not one, if many are there, then how to calculate the potential,
Yes,
like
sir.
q1, q2, q3, right here q1, q2, q3, and there is another one minus q4
Yes, sir.
at some point. Okay, now so this distance is, let us take this distance as r1, this distance as r2, this distance as r3, and this distance is r4.
Oh,
Then potential at point P, let us take this point as P. Potential at potential at point P is equal to potential due to first charge plus potential due to second charge plus potential due to third charge plus potential due to fourth.
oh,
How many charges are there? That many. We
yes,
need
sir.
to add them algebraically because this electric potential is a scalar quantity.
Yes, sir.
Is a scalar
Quantity.
quantity. It is not a vector.
Yes, sir.
Okay. So now here I will write kq1 by r1 is v1
Yes, sir.
plus kq2 by r2 is v2 and kq3
By
by
R3.
r3 is v3
Yes,
plus
sir.
kq4
K3.
by r4 is v4. So
Before.
that's the potential at the point P. Now
Sir.
here negative charge is there, so I will write here minus.
Yes, sir.
So for the system of charges, we can write V is equal to K Qi by Ri sigma I is equal to 1 to n if n number of charges are there.
Yes, sir.
Okay.
Yes, sir.
Okay. Then electric potential due to system of charges also we did. Now we will calculate for different potential due to different bodies. Like infinitely long conductor, the potential is going to be for continuous. So this is for point charge. This is for
System of
system
charges.
of charges. Now I'm going to write for a continuous charge distribution. Potential potential due to potential due to infinitely long conductor, infinitely
Long.
long conductor. For potential due to infinitely long conductor, V is equal to minus lambda by 2 pi epsilon naught,
R.
okay, log R base E plus C.
Yes, sir.
Okay, this is the potential. Now,
Yes, sir.
next one, potential potential due to a charged ring, potential due to a charged ring.
Ring. Yes, sir.
Okay, now potential due to charged ring V. So if you take this as the ring and at a distance x, if you are finding out the potential at a distance x,
Yes,
if
sir.
this radius is r, then the potential at the point P is potential at the point P is equal to kq
By
by kq by root of r
R
square plus
plus X square.
x square.
Yes,
Okay,
sir.
and the potential due to ring at the center
Yes,
is, you have to put x is equal to 0. So potential at the center is equal to kq by r,
yes, sir.
kq by r. Now
R.
we have to remember that, okay, I'm writing capital R here, radius, so I'm writing capital R. Okay, now
Yes,
here electric field at the center, we got it as 0. Okay,
yes, sir.
here the potential we will get kq by r.
R. Yes, sir.
Okay, now so now this one is important. Okay, now potential due to a conducting sphere. So we did for infinitely charged conductor. From here it starts for continuous charge distribution.
Yes, sir.
Potential due to continuous
Charge distribution.
charge distribution. So we were discussing for continuous charge distribution. Okay,
Yes,
this. So potential due to infinite long conductor, potential due to charged ring. Then potential due to charged conducting sphere.
yes, sir.
Potential due to potential due to charged conducting charged conducting sphere.
Yes, yes, sir.
Potential due to charged conducting sphere. So now you consider a sphere. Consider a sphere. Okay. This charged conducting sphere. This is conducting sphere or hollow sphere. You have same equations.
Yes, sir.
Or hollow sphere, you get the same values because the charge, if you give for conducting sphere, it will always reside on the surface.
Surface.
Now, at a distance r outside, so let us take capital R as the radius
Radius.
and smaller as the
Distance.
distance of the point P.
Yes,
Okay,
sir.
now here the R value is greater than R, then V out is equal to 1 by 4 pi epsilon naught. This is K Q
Q
by smaller.
R. Yes, sir.
If R is equal to R, this is on the potential on the surface, that is equal to KQ by capital R.
Yes, sir.
Then we have potential outside, potential on the surface,
Surface.
potential inside, V in.
Yes, sir.
So R is less
Less
than
than.
R. Now for R less than R, we write potential is same as that of the surface, and which is equal to
KQ by capital R.
KQ by capital R.
Capital R. Yes, sir. Capital R. Yes,
So
sir.
here
Capital R.
inside it is KQ by R. Inside it is constant KQ by R.
Yes,
Now
sir.
electric field is zero when it is inside. Okay.
Yes, sir.
Potential is same on the surface. On the surface, so you have a question like on the surface, we have 10 volts. Then what is the potential inside? How
Yes, sir.
much? How much? What is the potential inside?
Same, sir. 10 volts.
10 volts. Important problem.
Yes, sir.
Okay. So now if you draw a graph between the potential and distance, you see inside it is constant. How much it is? KQ by capital R.
Capital R.
Up to R is equal to R, it is constant. And then you will have an inverse relation because V is inversely proportional to R from the surface to outside.
Yes, sir.
Okay, very important. Here you say the inside the sphere, the potential is constant.
Yes, sir.
Potential is constant
Constant. Inside this.
inside the sphere. Very important point.
Yes, sir.
Inside the conducting sphere. Okay, important. Have to be thorough with all the formulas.
Yes, sir.
Okay, right. Then non-conducting sphere. Now this is see, if you see electric field is zero inside, but potential is constant. This is also
Yes,
important question.
yes, sir.
For a charged conducting sphere, electric field is zero inside the sphere, but potential is
KQ
constant.
by R.
Uh,
Constant.
Potential is constant.
Yes,
See,
sir.
now when you write the relation between E and dV, then we write E is equal to minus dV by dr. See
Yes,
here,
sir.
V is constant. When V is constant, it is not changing. It is remaining constant. When this is constant, electric field will become zero. Constant differential is zero. So
Zero.
that's
Yes,
why
sir.
electric field is zero.
Yes, sir.
Okay. From this relation also we can put our argument.
Yes,
Okay.
sir.
Then and next one is potential potential due to potential due to conducting non-conducting. So I'm already we wrote for conducting. So
Yes, sir.
we will discuss about non-conducting sphere. So here if it is a non-conducting sphere, then you have, I mean, non-conducting sphere means it is made, the sphere is made up of paraffin wax. Okay, wax, and you got some charges embedded in it like this.
Yes, sir.
Okay, so now for this one, we get, so let us take our radius as radius as r, radius as capital R, and we will consider a point at a distance r.
Yes,
Then
sir.
potential outside, where this small r is greater than r, V out is equal to KQ
KQ by
by
smaller.
small r,
Smaller. Yes, sir.
and V on the
Surface.
surface is KQ by capital
Capital R.
R,
Yes,
and V in
yes, sir.
is potential inside is KQ into 3R square minus R square by 2R cube. Now V at the center is equal to, at the center means smaller is equal to 0. Then
Yes,
I
sir.
will write a KQ into 3R square by 2R cube. So it will give 3 by 2,
3 by
3 by 2 KQ
KQ by R.
by R,
Hello.
by R. That
Yes,
is nothing but 3 by 2 times of potential on the surface.
surface.
V at the center is 3 by 2 times of Vs, or else we can write 1.5 times of the potential of
VS.
the on the surface.
Yes, sir.
Okay, so if you draw the graph between the potential, and the distance, then we get something like, because its potential is 3 by 2 r,
Yes, sir.
so you get like this. Okay, this Vs potential on the surface. This one.
Yes, sir.
Okay.
Yes, sir.
So these things you need to be very thorough. You have to prepare a list of all the formula, and then you have to be very thorough. Read
Yes,
every day. It's not like one go. You should not read all of them. You learn again. You come back. You learn again and again. You come back and learn again. So every day you have to learn.
yes,
Okay.
sir. Yes, sir.
Now, okay, right. Now we'll go for the next concept, equipotential surfaces. Equipotential
Surface.
surface. Now you take a charged particle.
Yes, sir.
Now if you take a charged particle, now on this sphere, it creates an equipotential surface because charge is same, distance is same. That means every point on it will have equal potential. Say
Yes, sir.
at this point potential is kq by r, at this point also kq by r,
By
so it
R.
creates an equipotential
Surface.
surface.
Yes, sir.
Okay, now the is equal to work done is equal to uh, work now potential is equal to what we wrote, potential is equal to work done by unit charge,
Yes, sir.
right?
Yes, sir.
So W is equal to Q into V.
Into V.
V is the potential. So
Potential.
if you are taking the body from A to B, then
Yes,
work done in moving the body from A to B will become VA minus VB. Actually, it is V work done. V is potential at that point minus potential at infinity. Potential at infinity is 0. Okay. So original formula is Q into V minus VA minus VB. So if you are
maybe.
bringing from A to B, but right.
Yes, sir.
So W is equal to, now here you can see here that now here you can see that potential of A and potential of B are same. So the work done is 0.
Yes, sir.
So what we can write is the work done, the work done in moving a charged particle, in moving a charged particle, in moving a charged particle along an equipotential surface, along a equipotential
Surface.
surface, the work done in moving along an equipotential surface is 0.
0.
Okay, because the potentials will be same.
Same. Yes, sir.
Okay, now so based on this you have lot of questions like a charged particle is placed. Now this is A, this point is B, this point is C, this point is D.
Yes, sir.
In which case the work done is more.
Work done is 0.
Work done is 0. So work done from A to B is equal to work done from A to C is equal to work done from
A to
A
D.
to D, that is equal to 0.
0.
Why the work done is equal to 0? Because when you
Equipotential.
place a charge it creates an equipotential surface.
Yes,
Work
sir.
done in moving the charge from one point to another point along the equipotential surface is 0.
Yes, sir.
Along the equipotential surface is 0 because the potential difference will be same.
0. Same. Yes, sir.
Potential difference is same. Okay.
Yes,
Now,
sir.
right now, so if you have a charge here, then you have an equipotential surface. Then
Yes, sir.
here at a distance r2, you will have a equipotential surface. Now, there
Yes,
exists
sir.
infinite number of equipotential surfaces.
Yes, sir.
Okay. Now electric field lines, if you draw, then it will be like this. Electric field lines. Now you see the electric field lines are always perpendicular to the equipotential surface.
Yes, sir.
So you write that point. Electric field lines are perpendicular to equipotential
Equipotential
surface.
surface.
Okay.
Yes, sir.
Now see. Okay. Now so now you have a positive charge. When you have positive charge here, this positive charge will have field lines like this.
Yes, sir.
Okay. Now field lines like this. Now if you take a point here, this potential, let this point is A. Okay.
Yes,
Now let us take that this charge is positive. Now if this is positive, this will be repelling this positive charge, right?
yes, sir.
Against these repulsive forces, if you push the particle
Yes, sir.
from here to here,
Yes, sir.
from A to B, then the work is done against the repulsive forces.
Yes, sir.
Work is done against the repulsive forces.
Repulsive.
The work done against the repulsive forces is stored in the form of potential energy. That means the potential of B is greater than potential of A.
Yes, sir.
Against the field, if you are moving a positive charge, then potential increases.
Increases.
So you can just imagine, to better understand this, you just imagine a spring.
Yes, sir.
Now you take here the point as A. Now
Yes,
you push this A. When you push the A from there to here, then what happens? The work which you do in compressing the spring is stored in the form of elastic potential energy, whereas here it is stored in the form of electrostatic potential.
potential energy. Yes, sir.
Yeah, electrostatic potential
Potential
energy. So the
energy.
potential of the positive charge increases when you are moving from A to B. Again, as the field, the potential is going to
Increase.
increase. Again,
Yes,
as
sir.
the field.
Yes, sir.
Okay. Now, again as the field, if you move again as the field, the potential is going to
Increase.
increase. Okay. So
Yes,
now, if you take another point C, then we write potential of A is equal to potential of C.
C. Yes, sir.
But these two will be greater,
Less, less than
these two will be less than
potential of B.
potential of B.
Yes, sir.
Okay.
Yes,
And
sir.
now, based on this concept, he might ask you this. See, you can join this one, and he can ask you, okay, which has got greater potential.
Yes,
Okay.
sir.
Now, the same thing, a slightly different approach. Now, I will take an electron. Okay.
Yes,
Now, this is positive, and so it creates uniform electric field. In this electric field, if you leave an electron here,
yes, sir.
if you leave a electron here,
Yes, sir.
negatively charged particle here, then it will move in this direction.
Yes, sir.
Now here work is done by the field. I
Yes,
mean,
sir.
okay. So work is done not by the external force, it is by this one. So
Field.
what
Yes,
happens
sir.
here is the potential decreases.
Decreases.
If this is electron, then potential is going to decrease.
Decrease.
If it is
Yes,
having
sir.
negative charge, then potential of A is greater than potential of
Potential of
B.
B. Yes, sir.
Okay.
Yes,
Now
sir.
here what happens? Potential
De- decreases.
decreases.
Yes, sir.
Your potential decreases. Now in this case, I took a positive charge and moved from here to here. So or else I can say I have projected a positive alpha particle from here to here. Then its kinetic energy decreases and potential energy
Increases.
increases. So
Yes,
the
sir.
loss in kinetic energy, half
Yes,
m VA square
yes, sir.
minus VB
B.
square. I will use conservation of energy here. There is
Yes,
a
sir.
loss in kinetic energy. The
Yes, sir.
loss in kinetic energy is converted into gain in
Potential
potential energy,
energy.
or Q into VB minus
We.
VA. VB has
Yes,
got
sir.
greater potential.
Yes, sir.
Okay. So the potential energy converts into the kinetic energy converts
What
into potential
potential energy.
energy.
Yes, sir.
Here what happens? Here the velocity increases.
Yes, sir.
Here the velocity increases. So here I
Increases.
can write half m. Which velocity is more? Velocity at B will be more.
B greater.
VB square minus
VA square.
Q square is equal to Q into
Q
the
into.
difference between the potentials.
Yes, sir.
VA minus
Minus VB.
VB. Whichever is greater, that one, from that we will. I
Yes,
will
sir.
subtract. Okay,
Yes, sir.
right. Then relation between, done, right? Understood these
Yes,
concepts?
yes, sir.
Okay. Then relation between electric field and potential. Electric field and potential. Now E is equal to minus dV by dr.
Yeah. Yes, sir.
Minus dV by dr. Now from here you can write dV is equal to minus E dot dr.
Yeah.
So you write integral on both sides. Then
Yes, sir.
V is equal to minus integral of E dot dr.
Yeah.
Okay.
Yes, sir.
The same thing here. Mm, dV by dr, what does it mean? So if you have electric field here, then it will produce electric field lines like this. Now here, this is V2, or say this is V1. This is V2.
Me too.
Now, okay, test charge is always positive. So here V2 is greater than V1.
One.
Okay, now as we have discussed, now imagine a string here, a spring here. Now if you compress it, that means if you do work, the work
Yes, sir.
done is stored in the form of potential
Potential and
energy. So per unit charge, it is potential. So, okay,
yes,
potential
sir.
energy increases means potential increases.
Yes, sir.
Then here V2, V1. Okay, so here let us take this distance is D.
Yes,
This
sir.
distance is D. Then we will write this one as electric field is equal to minus of V1 minus V2 by, now let us take this as R1, this is R2. So this is R1 minus R2. So this one we write it as uh, minus, this is V2
Mhm.
minus V1. Okay, now this we can say, this we write it as minus dV by dr.
Yes, sir.
Okay, or else that difference in the potential by d, or simply E is equal to V by d. The potential, if I took V as the potential uh,
D.
difference. Okay,
Yes,
now
sir.
you see here why minus we got, because here electric field
Again,
and yeah, so in opposite to the electric field, if you travel, then potential increases.
increases.
In the direction of electric field, potential decreases.
Decreases.
Okay,
Yes,
here
sir.
if you write V2 minus V1, then we will get plus only. But here in the direction of electric field, potential decreases. To denote that, we wrote minus.
Yes, sir.
Okay, E is equal to V by D also we can use if the electric field is constant, right?
So
Now
D is
again,
distance.
yeah, D is the distance between the
Two
2 points.
point. Yes, sir.
Yeah. Yeah. Okay.
Yes, sir.
Now, E is equal to dV by dr. If you want a electric field along a x-axis, then we write minus dvx by dx
Yes,
I
sir.
cap. If you want along y-axis, dvy by
Fine.
dy.
Yes. Yes, sir.
Ez is equal to dv
D
put z by
DZ.
dz.
Yes, sir.
Okay, right. Say electric potential, like the problems will be like this. Say the potential is given as 4x square. Okay, so the electric field at a point, find the electric field at a point 1 comma 0 comma 2. Then
Yes, sir.
electric field E is equal to minus dV by dx. Now here I am not writing dy and dz because only x variable is there.
Yes,
If
sir.
I write, so this term will become 0 and this term also will become 0
Zero.
because there is no y term and z
Yes,
term.
sir.
If y term and z term are there, then I would have written this one.
Yes,
Okay, Ex and Ey and Ez also I would have written.
yes,
So that is equal to differential of d by dx of minus d by dx of 4x square. If you do, then how much you will get? 8x
yes, sir.
minus 8x
Yes, sir.
minus 8x. That means x value is 1. So
Yes,
that
sir.
is equal to minus 8.
Eight.
Okay,
Yes, sir.
minus 8 volt per meter. From here, dV by dx, V is volt, x is in meter, so minus 8 volt per
Meter.
meter.
Yes,
Okay.
sir.
Now, if you have like 5x square, let's take another example. 5x square plus 10x minus 9 is potential V. Then now here you have Ex. Ex is equal to dV by dx.
EX. Yes, sir.
That is equal to uh,
Then plus 10.
d by dx of, no, here also y term is not there, no?
Yes,
Okay,
sir.
5x square plus 10x
10.
minus 9.
9.
So this is
10 by
10x plus 10,
10. Yes, sir.
right?
Yes,
And
sir.
here, what is the values? Here values are, let us take this as at x is equal to 1 meter.
Yes,
Okay.
sir.
So this is minus 10 plus 10. Oh my, so minus of 10 plus 10 minus 20 volt
20
per
per
meter.
meter. Yes, sir.
Okay, this is also important model.
Yes, sir. Sir, YZ
Yeah.
variables ఉంటాయి sir.
YZ variables are there, then you have to do differential with y and x also.
Yes, sir.
Oh, we will do one then. Let us take one 4x. V is equal to, simple one I will give you, 4x plus 3y.
Yes,
Then electric field along x-axis is equal to dV by
yes,
dx minus dV by dx. Minus d by dx of 4x, only 4x 4x plus 3y. Now that is only differential is only this x only we can differentiate. So this term is minus 4
yes,
minus 4 I cap, because this is like ex. Then
yes.
ey is equal to minus dv
DV
by
by
dy.
DY.
That is equal to minus d by dy of
4
4x plus
3y
3y. So that is equal to minus 3j
C cap.
j
Yes, sir.
cap. So E is equal to Ex I cap plus Ey
J cap.
j cap. That is equal to minus
Minus
4 I
4
cap minus 3
3 J cap.
j cap. Okay. Then as
Minus
these are perpendicular, you get 5 volt per meter because root of 4 square plus 3 square, that is equal to root of 16 plus 9, that is equal to root 25, that is equal to 5 volt per meter, 5 volt per meter.
so screen కనిపించట్లేదు సార్. ఇప్పుడు
Yeah, yeah.
yes sir.
Right now, yeah. See, another important one is potential due to ring. Already we have discussed this important model question. So now here you have a ring, and here you have another ring. Two rings are there. This radius is r. This radius is also r. The distance between them is also r.
Yes sir.
Okay. These are identical thin rings. Whenever he says identical, that means the radius is same.
Same. Yes sir.
Okay. Now here the charge here is Q1 and the charge here is Q2.
Q2.
Okay. The charges are uniformly spread on the two rings. The work done in moving a charge Q from center of one ring from here to here. What is the work done in moving the charge Q from one point to another point, from here to here? Okay. Let us take this ring center is at A and B. The work done in moving the charge from A to B. Now, obviously, our answer will be work done will be equal to this Q into VA minus VB. So that is our answer. So first we have to calculate the potential at A and the potential at B. Now the potential at A is equal to the potential at A is potential due to this ring plus
Yes sir.
potential due to this ring. Potential at the center due to this charge
Yes
is
sir.
KQ by R,
R. Yes sir.
right? KQ1 by R plus potential due to this charge due to this ring at A is
Yes sir.
KQ2
Q2 by R.
by root of R square plus R
R.
square plus X square. X square is also R, so R square plus R
R.
square. Then potential at B, potential at B is equal to potential due to this ring.
Yes
Potential
sir.
due to that ring is KQ2
Q2
by
by
R
R.
plus potential due to this ring at this point, that
Yes sir.
is KQ1 by root of R square plus R square.
R square.
So, so now if you do this one, then here you will get KQ1 by R plus KQ2 by this is 2R square. So this is root 2 R. Now
Yes sir.
here KQ2 by R
R.
plus
KQ1 by
KQ1 by
root
root
2 R.
2 root
R.
2 R. Then you have to substitute potential of A minus B. So that gives us Q into Q into VA. VA is K
K
Q1
Q1 by
by
R.
R plus
K
K
Q
Q2 by
root
root
2R.
2R minus
K Q2 by
Q2
R.
by R minus K Q1 by root
Mhm.
2 R.
So
So
plus
that
का
is
check
equal
करो.
to Q into minus is there here.
Okay sir.
This minus this.
Yes.
Minus of in brackets here
Hmm.
plus then you will
Hmm.
get minus and minus
Yes.
here. So if you simplify this one, you'll get root 2 minus 1 into q1 minus q2 by 4 pi epsilon naught r into root 2.
Yes sir.
This is the work done.
Yes sir.